simulations is what it's called, but really we're talking about probability. You've done probability before. I guarantee you have. Okay, the two types of probability we need to talk about are experimental probability and theoretical probability. Okay, starting with theoretical. Theoretical is based on facts, exactly how many outcomes there are, exactly how many are favorable. Okay, so it's the number of favorable outcomes to the total number of outcomes based on facts. So the example they give here in the reading is if you have a coin, heads or tails. There's two total outcomes. If it lands on heads, there's one head for two total outcomes, so it's 50%, one half or 50%. We're going to get in the habit of writing our probabilities both as a reduced fraction and as a percentage, okay? So the theoretical probability suggests that 5 out of 10 tosses will most likely be a heads up, but that's not a guarantee. So if you did an experiment with a coin and you flipped it 10 times like they did right here, and they got 3 heads and 7 tails, okay, well, it's not 50% because it's an experiment. Now, the more you did it, if you flipped that coin 1,000 times, you would be closer and closer and closer to 50%. But when you're talking experimental probability, you are basing your numbers on an experiment. What happened in the experiment, as opposed to theoretical is what are total possibilities and what are our favorable outcomes. So that's the difference. All right, so right here, let's look at this first example. It says find experimental probability. So a die is rolled. That would be like a number cube with 1 through 6 is on it, and they rolled it 50 times, and here are the results. So what is based on the experiment, so find the experimental probability, so these are the numbers we are going to use, of rolling at least a 5. Okay, well, probability of at least a 5, that would mean I could do 5 or a 6, so there were 6 of those outcomes, 7, so a total of 13 times out of 50 that it was, oops, there it is, out of 50 that it was a number at least 5, so 5 or 6. So I'm going to write it like that in reduced form, which is that because and then 0.26. I know I said as a percent, but really I meant as a decimal. Okay? Then, what is the probability that it's even? Well, that would be a 2, a 4, or a 6. So we add those up. 10 plus how many 4s? 7 plus how many 6s? 7 over a total of 50 outcomes. So it's 24 over 50, which I can reduce by 4. No, excuse me. I can't reduce by 4. I can't, so it would be 12 over 25, or 48%, or 0.48. So I'm going to give both of those answers. Oops, sorry about that. 1 or 2, that means a 1 is acceptable or a 2 is acceptable. So 6 plus 10 would be 16 over 50. That one was going to be 8 over 25, which as a decimal is 0.32. And last one, just a 3. So 14 over 50, which is 7 over 25, which is probably going to be 28.28. Yep, there it is, 0.28. So that is finding their probability based on an experiment. That is experimental probability, using the numbers that you get from your experiment. All right, that's pretty much it. And then they're going to ask you to compare those to, you know, how many times in theoretical probability for all of that would be, you know, at least a 5 would be 2, that would be 1/3. So 33%. So a little less. You probably should have anticipated a few more of those, but that's essentially your worksheet. And that's what I'm talking about right here. It says, notice the experimental probability of rolling a 3 was 7 over 25, 28% right here. Well, we know that it's actually 1 out of 6, which is 16.7%. So theoretically, you expected it to happen. It happened more than you expected it to happen. But that's because it's an experiment. Remember, the more you do this, the likelihood that it will become closer and closer to the theoretical becomes better. okay? So a simulation is an experiment. If you have an experiment or something that would be very difficult to perform, or maybe it would be impractical, you can't set it up, you could set up a simulation. So using a model, it recreates the situation with the same probability so that you can make a predicted outcome. So it's a mathematical model to use. Now, most times, if there's two chances, they'll use a coin or dice. Now, remember, we are familiar with the cube dice, so there are 6 sides, but they make dice with all sorts of sides. You can get a 7-sided dice, a 5-sided, 10-sided, 8-sided, all over. Random number generators you can get on your computers. If you have a cell phone, they have an app that is a random number generator, or any other kind of thing. You can put marbles in a sack of different colors to represent different things. So you could design a simulation. So step 1, determine each possible outcome and its theoretical probability. And then you're going to have to come up with a model to represent the exact same theoretical probability of that situation, and then define how many you're going to do in the trial, how many trials you're going to conduct, and how much time, so you can make a prediction. Okay, so let's think about this. I'm not going to really write this down, but I do want to talk about it. So what if they asked you to design a simulation? A survey asked the team of executives for which team they thought free agent Bonnie Solomon would choose to play for next year, and there are the results. So 30% of them thought it would be Cleveland, 60% in Miami, and only 10% in New York. Design a simulation. So I looked at this and went, oh, they're all multiples of 10. So I could represent this with 10 different marbles and make one of them a specific color that represents New York, 3 of them a specific color that represents Cleveland, and then 6 of them that represents Miami. Throw all those marbles in a sack or something, and just start pulling one out, record it, throw it back in, shake it up, pull one out, record it, throw it back in, and shake it up, and you could create a simulation, which you're going to do on your assignment today, kind of. Hopefully you brought a deck of cards, okay? Conduct and evaluate a simulation. So here we go. Eloy? I feel like maybe they forgot the R. Elroy? Anyway, this guy inspects bike frames as they come through the assembly line. From previous observations, he expects to find a weld defect in 1 out of every 10 frames and a design defect in 1 out of every 20 frames that he inspects. Design a simulation using Eloy's expectation of defects and assume that a frame can only have 1 of the defects. That's an interesting, that actually makes it easier. So when I was thinking about this earlier, okay, so one says out of 20 and the other one says out of 10. I can incorporate all of that. I can make 20 coins or 20 items, all the same, maybe marbles or what I like to use. And then in that, 1 out of 10 would be represented by 2 in my 20. So to represent the weld defect, which is 1 out of 10, I would put 2 of a specific color in there. That would represent the weld defect. And then 1 out of every 20 for the frame defect would be a different color, and I would only have 1 of those. So in there I'd have 20 marbles, 2 of one color represents weld defect, and 1 of the other color represents the frame defect. I'd put them all in a bag or something I can't see, and I'd take 1 out at a time, record it, place it back in there, and then again, draw again. So that's what I would do. I would probably do it 50 times. They did one 40 times. And here we are. We're going to calculate the experimental probability. So 3 out of 40, which is 7.5%. 2 out of 40, which is 5%, and 35 out of 40, which is 87.5%, and then actually put it into a bar graph for you. So you will have a situation like that where I'm asking you to do something with the deck of cards on your worksheet, but that's all I've got, okay? Making sure you understand the difference between a theoretical probability and an experimental probability. Remember, experiment needs just that, an experiment to take the numbers from. Other than that, You guys should nail this. It's a really short worksheet. Come see me if you have any questions, and good luck.